Hey, 6.2, big idea. Properties of exponents still work with rational exponents. We've spent a lot of time in chapter 5 looking at these properties. We'll review a few of them here with rationals. First off, when you have the same base, you're adding exponents. Gets a little bit trickier with fractions because you have to have the same denominator. These already do. So you have 1/2 plus 3/2 is 4/2, which we simplify down to x squared. Power of a power, you're multiplying. We did a little bit of this in our previous video. You're going to multiply 4 times 1/3, so it turns into x to the 4/3. Just so that we're clear, and this will help us in the future, we could rewrite this as x to the 3/3 times x to the 1/3. The reason that can be helpful is because this could be simplified to just simply x then times the cube root of x, and we've simplified our radical. Finally, we'll put a couple of things together. First off, remember that a square root can be written as a fraction exponent, 1/2. We can also move this to the numerator if we change the sign. And so we would say this is going to be 2 and then times 3x minus 1, to the negative 1/2. And again, we talked briefly last video about how that can be useful down the road, getting rid of a fraction. Just one more way to kind of simplify things. Okay, big idea number 2. You simplify radicals according to the power. We have done this before where we've simplified square roots. Square roots are easy because we know perfect squares. If you look at 147, I like to try to find the biggest perfect square. So we would factor this, and 147 is divisible by 49. It's 49 and 3. So you rewrite 147, square root of that, as the square root of 49 times the square root of 3. And the square root of 49 is 7, and the square root of 3 we just leave as 3. Well, that gets a little bit trickier when we do cubes because we just don't know cubes as well. But you're looking for the same thing. Here's 189. We have the cube root of 189. And we have to try to find a perfect cube in there. And that's not as easy because we just don't have those memorized as well as we do the squares. So you can always just factor. So take 189 and divide by 3. It's not divisible by 2, so we might as well try 3. And it is divisible by 3, so we get 3 and 63. And then I know that 63 is divisible by 3. 6 plus 3 is 9, and that's divisible. So we've got 3 and 21. 21 is divisible by 3 and 7. So now I look and I just try to find triples, essentially. I notice that I've got 3 times 3 times 3, which rewritten is simply 3 to the 3rd. And then it's multiplied still by 7. And so we have the cube root of all of that. And you can check on your calculator, 3 to the 3rd times 7 is in fact 189. Well, our properties say that we can split these up. So it's 3 to the 3rd times the cube root of 7. Obviously, we know that cube roots and roots are going to cancel. They're inverses of each other, leaving us with 3 on the outside and root 7 on the inside. So just, simplify according to the power. Don't feel like you need to be looking for perfect squares, only in square roots. So now as we go beyond, we have to broaden our approach a little bit. Variables is really not that much different. You're looking for perfect squares, and so you look at this one and you treat this 18 the same way. With square roots, I feel like we're stronger, and so you can look at this and say, okay, I've got a 9 and a 2. So I'll begin to rewrite this as the square root of 9 times 2. And then we look at x to the 3rd, and you can break that into x squared times x, all right, simply breaking up that x cubed. And then finally y to the 7th. This will break a couple more times, but you're just looking for a perfect square. So it's y to the 2nd, y to the 2nd, y to the 2nd. That's a total of y to the 6th right now. And then we will have just a lone y left over. So we're kind of breaking it apart into easier to find pieces. And then we would just essentially take out what we can. We know that the square root of 9 is 3. The square root of x squared is x. The square root of y is y. This y squared. That's y, and that's a y. So we still have 2x and y on the inside of the root. That's not going to go away. 2xy still stays there. But now in front, we've got a 3, an x, and a y to the 3rd. And now this is our simplified answer. I'd pause it now and see if you can try this one on your own. I'll get started though. 64 as far as now perfect cubes. If you don't know the perfect cubes, you can just start dividing this. 4 is a good place to start. It's 4 and 16. 16 is written as 4 and 4. So 64 is a perfect cube. We can rewrite that as the cube root of 4 to the 3rd. And then y, we can rewrite that as y to the 3rd times y to the 3rd times y. And now we just evaluate these things. The cube root of 4 to the 3rd is just 4. Y and a y. So we do still have just a y underneath the root. So we have a 4y squared in front and a cube root of just y left on the inside. Now there are some shortcuts you might start to recognize. You're kind of dividing in a way. If you notice that this is a y to the 7th here, and you are taking a cube root, right? If we just focus on that, you're really taking y to the 7th, and then you've got that divide by 3, right? Because cube root is 1/3. So 7 divided by 3 is 2 with a remainder of 1, or 2 and 1/3. So that's exactly what our exponents are. We have a 2, and then it's a 1 with that 3 as our exponent. So you're essentially asking how many pairs of 3's can I take out of 7. So if we go one more example here and think about if I ask for the 7th root of x to the 100th. All right, do I need to write out x to the 7th, x to the 7th, x to the 7th, x to the 7th? No, I don't need to do that. I can take 100 and I can divide by 7, and I know that 100 divided by 7 isn't going to be a perfect number. It's 14.2. Okay, well, I can take 14 groups of 7 out. So I can take x to the 14th. I can take out x to the 14th. But now how many do I have left on the inside that I couldn't? Well, 7 times 14 is 98, which means I have 1 left over on the inside. Another way to think about it, all right, let me see if I can break this down even more. We've got a 7th root of x to the 100th. Let me rewrite that as x to the 14th all to the 7th, multiplied by x to the 2nd. So 14 times 7, that's our 98. And then x to the 2nd is that 2 more, so a total of 100. Now we know that roots cancel with powers. That 7 would cancel with this 7. And so you have the x to the 14th in front, and then it's still x squared on the inside. So let's see if we can do some of those shortcuts here. 4 is not going to have a perfect square, so it's staying. How many times does 4 go into 8? It's going to be twice. So I'll have an a squared on the outside, and all of those are going to go away. How many times does 4 go into 10? Well, it goes in twice, so I'll be able to take a b squared, but I have a leftover 2. So underneath my root, I will now only have b squared. And then finally, how many times does 4 go into 6? It goes in once. but I have a c squared left over still inside. I was only able to take one group of 4. So now I can rewrite my final power here, 4b squared and c squared. So a little bit shorter than having to write them out, though you can still use that approach anytime. All right, 486. I'm going to use my calculator to start dividing that. 486 divided by 2. That looks to be about all we can get out of that. 2 and 243. This is divisible by 3 to 81. That's divisible by 3 and 227. And it just keeps working down. 3 and 9, and finally 3 and 3. So 1, 2, 3, 4, 5. A total of 5 3s. So I should rewrite that right away. The 5th root of 2 times 3 to the 5th, and then it's x to the 12th, y to the 7th. So we're trying to take out groups of 5. Can't take any out of the 2. I can take all of the 3's out. That's one group of 5 there. I can take 2 x's, x squared, but that leaves me with an x squared still on the inside because I have taken out 2 groups of 5. That's 10. And I can only do that once with the y, so there's a y out there. And this also will leave me with 2 on the inside. And there you have it simplified. One other idea about radicals is that much like we have with variables, like terms, you've got like radicals. Like radicals can be added and subtracted. Here you've got 3 root 2's added to 6 root 2's for a total of 9 root 2's. These two terms, on the other hand, could not be simplified until you simplify the radicals. So we're looking for a cube inside of 54. Well, 3 cubed times 2, that can be simplified then to 3 cube root 2 minus cube root 2. 3 cube roots 2 minus 1 cube root 2 will leave us with 2 cube root 2's. So you can only combine radicals if they are identical underneath. Everything has to be the same. All right, our last idea here is rationalizing a denominator. Rationalizing a denominator, we've done this before as well with square roots. Similar process when we start looking at cubes and things like that, but we'll take a look at how we did this with square roots. Remember, we can only multiply by 1, and we choose our 1 very carefully as the square root of 5. The reason we did that is because 5 times 5 became the square root of 25. And the square root of 25 is just 5. And then up top, now we have 3 root 5. If you try to do that same thing with a cube root, and you multiply top and bottom by that same thing, you won't get an answer you like because the cube root of 4 is not a nice number. So what you have to do instead is you have to make perfect cubes. So I have a 2 to the first. We need a 2 to the third. So I'm lacking a 2 to the second. Now this becomes the cube root of 2 to the third, which is just 2, and in my numerator, 6 times the cube root of 2 squared, which you could write as 4. How about this one? We've got a 5th root. We want something we can find the 5th root of. Well, 7 is bigger than like a group of 5. What's the next biggest thing? Well, how about 10? So what we're going to do top and bottom here, 5th root of y to the third. 5th root of y to the third. See, what we want to do is we want to make this nice. We can go up as high as we need to, and we went up to the 10th. Well, I know how many groups of 5 can I take out. I can take out one group of 5, so that turns into y squared in the denominator, and up top we have 6, and it's the 5th root of y cubed.